Hello and welcome to this video, where we will be exploring two questions on the Mathematics Extension 2 topic of 3D vectors and further integration. In this video, we'll be going over the work solutions for these questions, as well as the mark allocation for the questions, and alternate solutions, as well as any common errors, knowledge barriers, or tips that may help us overcome any issues found in the question. Starting with the 3D vectors question, we can see that this is question 16 of the paper, the last question. These questions typically target A3 and A4 responses. These require rigorous mathematical ability to fully answer correctly. Starting with part 1, we're given that the point XYZ lies in the sphere radius 1 centered at the origin. We can note that this is the unit sphere, much like how the unit circle is the circle of radius 1 centered at the origin. We are given the vector OP of xi plus yj plus zk, and we're asked to use the triangle inequality, or otherwise, to show that this inequality holds true. Looking at the mark allocation, we see that it is 2 marks. This is particularly important as it gives us the level of depth that the question would require. Us being given the triangle inequality to use to solve this question is a good starting point. Looking at part 2, we're given the two vectors A and B, and we're asked to show that this inequality holds true. Looking at the left-hand side, we can see it is quite similar to the dot product, where between the vectors A and B, where we multiply each term across and add them. Looking at the right-hand side, we can see that it was also very similar to the dot product, where it is a magnitude of A and a magnitude of B multiplied together. We're given that this question is 3 marks. This is particularly important as it gives us a sense of depth in the question and how we should go about answering the question. In part 3, we're re-given the statement provided in part I. We're asked to use part 2 or otherwise to show that this inequality holds true. This question is given as 2 marks to show that this inequality holds true. This would be because we are given a solution path to get this answer. Although we are given the solution path of using part II, we can also find alternate routes which we will be exploring later. Revising what the triangle inequality is, we're given that the sum of 2 sides of a triangle is greater than or equal to the third side of the triangle. We know that it can be greater than or equal to in this case as we're dealing with vector relationships. As the height of the triangle approaches 0 and gets closer to C, we can see that the overall magnitude of A and B will also decrease, approaching the length of C. This will become a straight line where this part is A and this part is B. Starting with part I, we can deduce, as previously said, that point P is on the unit sphere. We are given our first mark in the question for obtaining that the magnitude of OP is 1. We can restate this as given OP is xi plus yj plus zk. From our triangle inequality, we can then rewrite this thing that 1 is less than or equal to the magnitude of xi plus the magnitude of yj plus zk. We know this statement holds true through our triangle inequality as demonstrated in the diagram above. We can then rewrite this in saying that this is greater than or equal to our magnitude of xi plus a magnitude of yj plus a magnitude of zk, once again from our triangle inequality. And then as I, j, and k are both unit vectors, which is covered first in the Extension 1 course of vectors, we know that this statement is equal to the magnitude of x plus magnitude of y plus the magnitude of z. And therefore concluding, we can say that a magnitude of x plus magnitude of y plus magnitude of z is all greater than or equal to 1. where we gain a second mark for completing the solution. Alternatively, we can once again state that P is on the unit sphere. So therefore, using our magnitude expressions, we know that this holds true, as once again it is just a restatement of this. We can then say the magnitude of x squared plus the magnitude of y squared plus the magnitude of z squared is equal to 1 from this. We can also then say that our magnitude of x is less than or equal to 1, the magnitude of y is less than or equal to 1, and the magnitude of z is less than or equal to 1. Multiplying through by each term's magnitude, we gain the expressions that the magnitude of x squared is less than or equal to x, and the same thing for each other term. This is where we gain our first mark for finding the relationship between the magnitude of x squared and the magnitude of x, and for all of the other terms. We know from above that each of our terms' magnitude squared is equal to 1. If our magnitudes are greater than each of these terms, then we know that if we replace the magnitude of x squared with the magnitude of x, respectively for each of the other terms, we know that this expression will be greater. Therefore, we know that the magnitude of x plus the magnitude of y plus the magnitude of z is all greater than 1. This is where we gain our second mark for the correct solution. I would recommend with going with solution path 1, as it is much easily seen, as we're given an instant direction from the question to go with a triangle inequality solution. This makes it easier to find marks within the question, especially at the back end, where questions are starting to ramp up in difficulty. Moving on to part 2, we can start with our dot product, which is straight from the reference sheet. We know that the dot product between two vectors is equal to the magnitude of the two vectors times cos of the theta between the vectors. This is straight from our reference sheet. We get our first mark for applying the dot products of these two vectors. We know our dot product will be our two x values multiplied together plus the two y values plus our two z values. And this is all still equal to the magnitude of the two vectors times cos of the angle. We know for our regular cosine wave that our range is between -1 and 1. Therefore, for this particular cosine wave, we know that our amplitude will be between the negative of our two magnitudes and the positive of our two magnitudes, with our dot product expression in the middle. You can see this graphically, where our range will lie in between this area of the graph, with it maxing at our positive values and minimizing at our negative values of our magnitudes. From this, we can rewrite our expression as magnitudes, our dot product, which from this is also equal to this form of the dot product, which aligns to what we are asked for within the question, and our positive over magnitudes. We gain our second mark for obtaining the inequality between the magnitude and the dot product. Looking at this expression, we know that an absolute value function can either be positive or negative. From learning further functions in the Extension 1 course, we know that we could rewrite this expression as the absolute value of our dot product is less than or equal to the positive version. This is because our dot product is in between two values of equal distance. Now, finalizing the solution, we know that our magnitudes are also equal to our Pythagorean statements. Rewriting this, we get the above solution, which is what we require. This is where we find our final mark. Alternatively, we can go straight to the dot product in between the absolute value function. From this, we get our dot product is equal to the same thing as we had before, but just within our magnitude symbols. We get our same first mark for applying the dot product here. Using the first solutions, we know that our range of our cos graph is going to be within an absolute value function. Therefore, our range will be between 0 and 1 of a regular photon wave or of absolute value. We can see that it will bounce and bounce off that instead of continuing and reflecting. Because we know our range is between 0 and 1, we know that when you multiply the magnitudes, that because this is less than 1, we know it's bringing down the overall value of this entire number. Therefore, getting rid of the magnitude of cos theta, we know that the magnitudes of the two vectors is going to be greater than this. This is where we gain our second mark for the inequality from recognition of that this is between 0 and 1. Therefore, we can just rewrite what we had here as what is required and over here to what we need for our question to be answered. This is where we gain our final mark. I recommend using the ultimate solution here. Although it might be harder to initially find, it is quite easy to find if you recognise that this is your dot product of A and B in between an absolute value zone. Randomly, just dealing with the dot product within the absolute value, and if you recognise that this inequality will be below 0, bringing down the overall weight, which is typical from proof questions within the extension 2 course, you know that this inequality will hold true and bring your answer shorter, where this is roughly 6 lines, this is only 4, saving you precious time at the back of the paper. Now part 3, we can recognise again that P, X, Y, Z is on the unit sphere. From this we can regain our expression, which we get as if you square a number, it's always going to be positive. So it doesn't matter where your X values are here, even if there's the absolute value sign, it's always going to be positive, so we can rewrite this expression. We then know from this that, say, the point Q, X, Y, Z, or with magnitude symbols, is also on the unit sphere, as it is the same in terms of our substitution points, as this is our X value, this is our Y value, this is our Z value. From part A, we can substitute A as our point Q and B as our point 1, 1, 1. We gain our first mark here for a suitable substitution from part I. From here we get our inequality from part 2, where our magnitude of the magnitude of X plus the magnitude of Y plus the magnitude of Z is less than or equal to the magnitude of our vector B and the magnitude of our vector A. We know as defined that this is equal to 1, and then using this we know that that is equal to the square root of 3. We know that these three values are not negative, so therefore the overall absolute value can go away, therefore leaving us with the absolute value of X plus the absolute value of Y plus the absolute value of Z is all less than or equal to 3. This is where we get our final mark for the solution. Looking at an alternate solution, we can consider the quadratic mean, arithmetic mean of two values. If we let A equal the magnitude of X, B equal to the magnitude of Y, and C equal to the magnitude of Z, all for simplicity reasons, we can see that A squared plus B squared plus C squared is equal to 1, and therefore X squared plus Y squared plus Z squared is also equal to 1, as it is on the unit sphere as previously discussed. The quadratic mean of these three is the square root of A squared plus B squared plus C squared over 3. It is over 3 as we have 3 terms that we're squaring to make the quadratic mean. Quadratic mean of two numbers is not usually discussed within the Extension 2 proof course. However, it is nice to know in this instance. The arithmetic mean, however, is often discussed using the AMGM inequality, and it is that the sum of the three parts over the number of parts is our arithmetic mean. From this, take the square root of our quadratic mean and the square root of our arithmetic mean. We can see that it is a squared plus b squared plus c squared all over 3 minus the quantity of a plus b plus c on 3 all squared. From this, we know that we can split up our square terms and expand through, as seen in this step. Combining fractions, making sure we distribute the negative to the entire fraction, and multiply this side by 3 to make sure we get a common denominator, we can obtain this expression of a ninth 2a squared plus 2b squared plus 2c squared minus 2ab minus 2ac minus 2bc. From this, we can split our square terms into individual parts as well as our 2ab, 2ac and 2bc terms. From this, we can do simplifying into different terms that we can identify as perfect squares. From this, we know that a minus b all squared is going to be positive, as well as a minus c and b minus c all squared are also going to be positive. We know this because we're dealing with a geometric plane which deals with the real number system, and any number squared is inherently positive. Therefore, a ninth times a positive number is going to lead to a positive number. Therefore, we can say that our quadratic mean squared minus our arithmetic mean squared is greater than or equal to 0. Rearranging, we know our quadratic mean is greater than our arithmetic mean. This is where we'd gain our first mark for this alternate solution. Taking the square root of both sides, remembering that we don't have to take into account the plus or minus, as the definitions of our quadratic and arithmetic means include them, we can then rewrite them back into their original form, where we have our a squared plus b squared on c squared on 3 all under the square root is greater than or equal to a plus b plus c all on 3. We can recognise from above that this is our unit sphere term, which is going to turn into 1, which is now 1 on 3 all square rooted. This is still greater than a plus b plus c all on 3. Multiplying each side by 3, we see that a plus b plus c is less than or equal to 3 times the square root of 1 on 3. Bringing our 3 in, we know this is going to turn into a 9. The square root of 9 on 3 is just going to turn into the square root of 3. Therefore, a plus b plus c is less than the square root of 3. And turning back into what our original definitions of a, b and c was, we can then say that the magnitude of x plus the magnitude of y plus the magnitude of z is less than or equal to the square root of 3 as required. This is our correct solution. Obviously, I would recommend choosing solution path 1, as is directly related to the question, and to be frankly honest, I don't believe anyone under exam conditions will even remotely see this solution path as even reliable. Linking to other topics within HSC Mathematics, we can see that it requires key concepts from Extension 1 vectors, such as the dot product and magnitude. We can also note that algebraic manipulation is heavily needed. This is from our advanced functions topic at the start of Year 11. As well as our prelim Extension 1 topics of further functions, where we graph absolute value functions. This is particularly helpful in part I, where we need to consider the absolute value function of cos in our alternate solution. Our alternate solution in part 3 is very similar to what may be found in an Extension 2 proof topic question. Although it is very unorthodox, if you see it, it is a guaranteed way to get your 2 marks. As well as this, our alternate solution in part 2 uses similar concepts to our proof topic, where we discuss that the absolute value of collars, as it is between 0 and 1, is going to bring down the overall score of our 2 values. This is typical of an algebraic inequality proof used in extension 2. Moving on to our integration question, we can see that once again it is at the back end of the page bar in question 15. Once again, it will target E3 and E4 responses. Looking at part I, we're given that Jn is equal to the integral between 0 and pi on 2 of sine to the power of n theta d theta, where n is given with this expression. We are asked to show that this is the case. Immediately, this points out that we need to be using integration by parts. Looking at the mark allocation of 3, we know that it's going to be pretty in-depth and require complex mathematical thinking. For part 2, we're given the expression of In is equal to the integral of between 0 and 1 of x to the n times the quantity of 1 minus x all to the n, where n is still a positive integer. We're asked to use the substitution of x equals sine squared theta, or otherwise, to show that In is equal to this expression here. This is where the bulk of our marks are found, being 4 marks. We need to make sure we are being mathematically rigorous to ensure we maximize these 4 marks. We can see that our 2 integrands here and here are quite similar, only being different between the power of our integrands. Part 3, we are asked to hence or otherwise show that In is equal to this expression here for integers greater than or equal to 1. The word hence here is referring to using part I and part double I, and making sure we link it. Mark allocation of 2 here represents that we need to use this link, as we have previously built the foundational skills to answer this question. Starting with I, we can start with our initial statement of Jn as given in the question. We can rewrite this with the integral between 0 and pi and 2 of sine theta times sine n minus 1 theta d theta. Here we get our first mark for finding our factors of sine to the power of n theta. We know that this is equal to here as of our index rules, where a to the n times a to the m is equal to a to the n plus m. We know that our power here is 1, so since we're multiplying these two, if we add the powers, it simplifies back down to sine n theta. Applying integration by parts, we know that our u value must be sine n minus 1. We know this through our acronym of LIATE, where although both of them are trig, we know that our u value must be n minus 1, as if we try and integrate u minus 1 from our v dash value, we're in the same situation as we are currently in, but we're trying to integrate something with an unknown power. This gives us a clear direction of what our u value should be, and gives us a clear direction of where we can go. Applying our integration by parts, we know it is our uv dash is equal to our uv in between our two bounds, minus the integral of 0 to pi and 2, which is again our bounds, of negative cos theta times by our u dash expression here. The second mark for this question was found through applying our integration by parts through this middle tier. Being careful of our two negatives at the front here, we can then start to simplify down our first expression, subbing in our bounds. We know that sine pi on 2 is equal to 1. 1 raised to any power is going to produce 1 again. Therefore, our sine n minus 1 pi on 2 is equal to 1. We also know that cos of pi on 2 is equal to 0. Then, for our 0 bounds, we know that sine of 0 of anything is also 0. 0 to the power of anything will give us 0. Then we note here that our negative cos 0 is going to give us an answer of 1. Here we know that this is all going to boil over into producing an answer of 0. Coming back to our big integral here, we can see that our n-1 is just a coefficient. We can change our two negatives here into a positive, bringing our coefficient out to the front. We're left with our positive n-1 times our integral between 0 and pi on 2 of cos squared times sine to the n-2. This is promising, as in the question we are trying to find a minus to the n-2 term, where n is our power of sine. Continuing this, we can see that our Pythagorean unit circle identity, sine squared plus cos squared, is equal to 1. We can rearrange this, find that c squared is equal to 1 minus s squared. We can sub this in for our cos value. We know that this turns to 0, and we're still left with our n-1 at the front and our integral. Our cos turns into 1 minus sine squared theta times sine to the n-2 theta. Distributing this across, we get our sine n-2 minus sine n theta. This is again due to our index laws, where when we add these two, the 2's basically cancel and become just n. We can then split this using our identity here of the integral of f of x plus g of x dx is equal to the integral of f of x dx plus the integral of g of x dx. This is common knowledge found from the Mathematics Advanced course. Then, from splitting this up, we have our n-1 integral of sine to the n-2 theta d theta minus, and making sure we carry this n-1 term as we split the integral, a very common mistake, minus our integral from 0 to pi on 2 of sine n theta d theta. We can recognize that this is what the question defined as j of n. Moving to the next line, we keep our n-1, and we can recognize that this term is also j n-2, as our power term is n-2, and is what is j of n. We then get that this minus our n-1, j of n, is equal to j of n up here. Expanding our n-1, ensuring that we carry through our negative properly, we get n-1 j n-2 minus njn plus jn is equal to jn. We can see that our jn's here will subtract from each other, leaving us with 0, and we can add our njn to the other side, leaving us with this expression here. Dividing both sides by n, we can see that j of n is equal to n-1 on n, jn minus 2, which is what the question required us to prove. This is our complete proof, where we come up, where we get a uv minus our integral of v u dash. For part 2, we are given that in is this expression here. We are asked to use the substitution or otherwise to show that this expression holds true. Starting with our initial expression, we immediately use the substitution given. We know that dx d theta is going to be equal to 2 cos theta sine theta. This is from our chain rule expression of sine theta squared. We bring our power down, and then we multiply it by the chain, which in this case is going to be cos theta. We'll see in an alternate solution where we work with this as being equal to sine of 2x, which we can see from our reference sheet. However, in this solution path, we will proceed with our 2 cos theta sine theta. Subbing in our bounds, when x is 0, we find that sine squared theta is also equal to 0. Therefore, our theta value is going to be equal to 0. When x is equal to 1, we know that our sine squared theta is equal to 1. We can then say our theta is equal to pi on 2. Our negative solution here can be negated because of the square. We know that we can take square root without dealing with the negative as we deal with the primitive solution. We can rewrite in using our substitution of sine as from the integral between 0 and pi on 2 of sine squared theta to the n times 1 minus sine squared theta to the n times 2 cos theta sine theta d theta. We get this as we know dx is equal to this expression here. So then when we need to change our terms of substitution, we have to bring it back into here. Bringing this 2 at the front, we get that 2 times the integral of between 0 and pi of sine of 2n theta. We can see we just multiplied through using our index laws, times cos squared theta, which we know from our Pythagorean identity, to the n, cos theta sine theta d theta. We get our first mark here for providing a correct substitution from the given substitution in the question. From this line of working, we can bring it down to simplifying our answer. We get 2 times the integral of sine 2n plus 1 cos 2n plus 1. We get this as we distribute the 2n here, and as seen previously in the question from our index laws, we know that when you multiply through, we gain plus 1, as this is to the power of 1. This happens to both of our terms. From this, we can link it to our prelim for the trigonometry unit in extension 1. Found on our reference sheet, we know that sine of a plus b is equal to sine a cos b plus sine b cos a. This is our compound angles. When we have the same angle, however, we know that sine of 2 theta, in this case, is 2 sine theta cos theta, as what we had discussed up here. Dividing both sides by a half, we know that sine theta cos theta is equal to a half sine 2 theta. From this, if we take the 2n plus 1 out, we can then rewrite this expression here as a half sine 2 theta, or to the power of 2n plus 1. Expanding through, we get our 1 on 2 to the 2n plus 1, as this distributes to each term, times by sine 2n plus 1 2 theta d theta. Here we get a mark for getting our integral in terms of sine 2 theta. As n is just an integer term, we can bring this out the front and begin to simplify. We are left with 2 on 2 to the power of 2n plus 1 times the integral of sine 2n plus 1 2 theta d theta. We know we can split this into being 2 times 2 to the n times 2, where we can divide through by our 2's, leaving us with 1 on top. We are then left with the integral of in being equal to 1 on 2 to the power of 2n times the integral between 0 and pi on 2 of sine 2n plus 1 2 theta d theta. Here is where our common mistake happens in this question. A lot of students would leave it there, but we are asked to show that that expression is equal to sine 2n plus 1 theta d theta, not 2 theta. From this, we can use a substitution to deal with this 2 theta term. If we let u equal to 2 theta, then we know that du is equal to 2 d theta. Therefore, a half du is equal to d theta. Subbing in our bounds, theta equal pi on 2 means that u is equal to pi, as we multiply through by 2 here. theta being 0 does not affect our u value still being 0. Here we get a second mark for applying a new sub. Now we have our integral. When we bring this half back out, we can bring this to the power, as it's multiplying 1 on 2 to the 2n by 2. We get this term times the integral between 0 and pi of sine to the 2n plus 1 u du. From this, we can recognize what our sine wave will look like and the area under that sine wave. Between 0 and pi, we know that the area is going to be equal to 2 times the area between 0 and 2 pi. We know this because it is symmetrical around pi on 2. This extends the powers of sine, as when you square the sine wave, it won't affect the two y values, as they will remain consistent between the 2 points. On this side it will just flip, however it is negligible and we can ignore this side even though the areas will still be the same, as we're only dealing between 0 and pi. This relates to extension 1 and advanced area under curves, and especially our integral calculus with trig. It requires complex thinking and links with the further area and volume, and graphing further functions within extension 1. This is helpful, as if we bring it back to the question, we know that if we think of our integral as twice our integral from 0 to pi on 2 of our integrand, and splitting this back up into our 2 times 2 to the n times 2, we can see that these two 2's will divide out. From this, we have a half to the 2n times our integral of 0 to pi on 2 sine to the power of 2n plus 1 u du. Looking at this, we know that our original in statement we're looking for is our integral from 0 to pi on 2 of trig theta d theta. That is from above what we started with. If we think about it here, our variable and for our angle is within the bounds of theta and d theta. If we treat the theta as a dummy variable, we can bring it back in terms of theta. This is quite confusing for students solving this question, as above here we define u to be 2 theta, so why can we just switch back u equals theta? Initially this makes no sense, however as we're dealing with a definite integral, it makes complete sense. If we think of an example of an integral between 0 and 1 of 2x dx, we know that this is going to produce the same value of the integral between 0 and 1 of 2u du. Integrating this, we get x squared in between the bounds of 0 and 1 on both sides. However, on this side it will be of u. When you sub in your 2, you get your same value. So it doesn't particularly matter what variable you're using and with respect to what. So here we can switch back to our theta, which the question requires us, and we'll get our final mark for completing the proof. As previously mentioned, we have an alternate solution within this question. It is at the start of the question where we're given our bounds. It is at the start of the question where we're given our substitution, and we turn this value into our sine 2 theta, as what we previously discussed. Our two bounds will be the same for this question. Our two bounds will be the same for this question. The only thing that has changed is when we change our dx into terms of d theta, instead of this long expression, dealing with the sine 2 theta. Therefore, we have in is equal to this integral of sine to the 2 to the power of n times 1 minus sine squared theta to the power of n times sine to the 2 theta d theta. Then, doing simplifying here, we can see that our sine theta cos theta to 2n we can simplify from this. Doing what we did previously, but with a term of 2n up the front, we use our compound angles and we can create this expression here. We can then, as what we had previously done, bring our half to the 2n at the front, and we're left with sine to the 2n 2 theta times sine 2 theta left at the front. We can recognize that this is just to the power of 1, and then we're left with our sine to the 2n plus 1 2 theta d theta with our half to the 2n out the front. From here we can continue our proof as before. I would recommend using this alternate solution, as I believe it is more elegant and is a shorter approach and is easier to see that this relationship occurs. It requires less thought process in our applying our trig identities when using, and can lead to less errors. Finally, for part 3, we're given that we want to show that In is equal to n over 4n plus 2 of In minus 1. Starting out with our In term, from part 2, we can recognize that this expression is just j to the 2n plus 1 from part 1. We know this because our term, we can just sub our 2n plus 1 there, and it will be equivalent. From here, we can show this expression here is equivalent to the one above, using what we had shown in part I. From the expression here before, we know that In is equal to this, therefore multiplying by 2 to the 2n, we get that j to the 2n plus 1 is equal to 2 to the 2n In. If we let our n value here, here, and here equal to n minus 1, we can simplify down to find our jn minus 1 and our n minus 1 terms. This becomes particularly important as we sub back into our original equation here. Simplifying our third line down, we get 1 on 2 to the 2n times 2n over 2n plus 1, j to the 2n minus 1. Here we'll get our first mark for obtaining In in terms of jn. From this, we get 1 over 2 to the 2n times 2n over 2n plus 1 times what we had found over here as j to the 2n minus 1, we saw is equal to 2 to the 2n minus 2 times I to the n minus 1. This is promising, as in the question we are asked to put an I to the n minus 1 term in. Further simplifying this down, we can recognize that we can split this 2 to the 2n minus 2 term up into 2 to the n times 2 to negative 2. From this, we can see that our 2 to the 2n and our 2 to the 2n here will both multiply out to give us 1 as we divide them both. And then we can recognize that our 2 to the negative 2 is going to lead us with 1 over 4. And then we still have this term and our I to the n minus 1. We can recognize here that we have a common factor of 2 that we can cancel out. Then we are left with n on top and a 1 on 2 on the bottom here. We can multiply that 2 through to the 2n and to the 1, and we're hence left with In equaling n over 4n plus 2 I to the n minus 1 as required. We get our final for our complete proof. That we use our recurrence relationships to simplify down, which is what this is. It is a recurrence relationship. It is often followed with a certain n value like question, where it would be given, in this case, a part 4, where, say, we're given this expression here of In. We can say that we know that In is equal to this term, given we had already used part 3, and simplify down by subbing in n equals 5 here, simplifying it down to something that we can integrate and answer the question with. Linking to our other topics, there's a heavy reliance on integration from Advanced and Extension 1, particularly with trigonometric integration, using substitution, and in Extension 2, using the unknown substitution as what we had to use in Part A with our U value here. We can see that this would also relate to the nature of proof topic, and all these questions are asking us to build from the recurrence relationship to find the answer. We can see that we're also used to recognize the area under curves. That is particularly prevalent with integration within the advanced course, particularly with trigonometric functions in this case. We are also asked to use further integration functions and identities from the Extension 1 prelim course. After about 50 minutes of listening to me speak about Mathematics Extension 2 content on 3D vectors and further integration, I applaud you for making it to the end and listening to my amazing demonstration of the worked solutions and pathways that you can take while answering questions. I hope that this video has been enlightening and hope that you didn't fall asleep midway through. Thank you for listening.